Today we're going to look at rotational motion again in a little more detail. We're going to look at concepts of rotational kinetic energy and moment of inertia. So just as a quick reminder of the rotational quantities, there's the angular velocity, which is how many degrees per second the object is rotating through, and there's angular acceleration, which is how fast the angular velocity is moving. There's also these relationships between the angular velocity and the speed of a point a certain distance from the axis of rotation, and tangential and radial acceleration. Now, if you remember correctly, the equation for kinetic energy for a bunch of particles is a half mv squared for each particle. So you take the energy of each particle, half mv squared, you add them all up, and that would be the total kinetic energy for a bunch of particles. Let's rewrite this using, for considering several particles rotating around an axis together. So we're going to replace v with the rotational quantities, right? V equals omega r. So for each particle that is a distance r from the axis of rotation, and omega is it's how many radians per second it's going around. If I plug that in for v, here I end up with 1/2 m omega r squared, and what I can do is I can collect together the masses and the radii of each particle and pull out the omega, because they're all rotating together around the axis, so I can pull that out. So now we have 1/2 and then this quantity omega squared. We're going to call the quantity in parentheses, I like to call it the moment of inertia, but another word for it, and the textbook I believe uses rotational inertia. It is, the word inertia in there gives you a hint as to what it's about. It's a measurement of one way to think about it is the effective mass of the object as it's rotating. Remember, for regular motion, mass is a measure of how difficult it is to get it going, right? The more mass something has, the more energy it takes to get it going. Same thing with rotating. The more moment of inertia an object has when it's rotating around a certain axis, the harder it is to get it going. It's a measure of it's for a particular object or set of objects around a certain axis of rotation. Okay, so it's constant for a given object and a given rotational axis. So we're going to call this I, and so we can rewrite our kinetic energy as 1/2 I omega squared, and you can see this kind of looks like 1/2 mv squared. I is kind of like the rotational mass, and omega is kind of like the rotational v. And so for a bunch of point charges, I is this sum of the masses times their distance from this distance r here is the distance to the axis of rotation squared. So let's look. So these equations for a finite set of rotating particles, like I said, it corresponds to how difficult it is to change the state of rotation. The larger the moment of inertia it is, the harder it is going to be to change its motion. So let's look at some simple examples. Here I have a couple tennis balls. They're heavy tennis balls. They each weigh 0.5 kilograms. And I'd like to find their moment of inertia for each tennis ball if they were rotating around this axis. So we're sort of making the assumption that this tennis ball is sort of rotating around this axis, and then this tennis ball is also rotating around this axis. So let's find their moment of inertia separately. Okay, so for ball 1, let's write down everything that we know for ball 1. It is, let's see, its mass is given as 0.500 kilograms, and r for ball 1, how far it is from there, is this distance here. And we see, just reading it off the graph, that r1 is 2 meters. So we can calculate the moment of inertia, right? It's going to be, it's the sum of all the particles, but there's only the one in this case, so it's m times r1 squared. So 0.500 kilograms times 2 meters squared, and that works out to 2.00 kilograms meters squared. Now if I were to do the same thing for this ball here, so this ball is rotating like this ball here is different, right? It's not 2 meters. Its distance is, okay, well, it has the same mass, 0.5 kilograms. And its distance for R2 is 4 meters out. Don't worry about the minus 4r, it's just how far it is from the axis of rotation. So it's 4 meters out. And so if I go to calculate the moment of inertia here, it'll be mr2 squared So 0.500 kilograms times 4.00 meters squared. And when I plug in the numbers, I get 8.00 kilograms meters squared. So this is saying that the green tennis ball has a higher moment of inertia, or rotational inertia, than the yellow tennis ball. That's because it's rotating from further away. So if they tied to a string and tried to rotate around here, it takes more energy to get this thing going than to get this thing going. Let's do another example, but this time it's 3 balls rotating together. So let's assume they're all sort of attached to an axis here, and they're all rotating around the y-axis again. Okay, so if I want to find the moment of inertia of those 3 balls sort of moving together, let's start by saying, okay, well, the moment of inertia is going to be the sum of each mass times each radius squared, right, over all of them. And the first one, so it'll be 1 m1 r1 squared plus m2 r2 squared. So let's quickly look at how far apart they each are. So if I zoom in here, this one is 1 meter, right? This one here is 2 meters from the axis, and this one here is 1 meter from the axis. So I can now calculate how far, I can now calculate the moment of inertia. So m1 is 1 kilogram times m1's distance, which I said is 1 meter. We'll put in sig figs at the end. The second mass is 2 kilograms, and it's a distance of 2 meters away. The third mass is 3 kilograms, and it's only 1 meter away. So when I calculate all that, I end up with, let's see, 1 plus 8 plus the third one gives me 3 kilograms meters squared. Now it says find the kinetic energy if they're rotating around the axis at 2 radians per second. So they're all rotating around the axis together at 2 radians per second. So their rotational speed is 2 radians per second. Okay, so let's calculate. We can just use our equation for kinetic energy up there in the top left-hand corner. So our kinetic energy is 1/2 I omega squared. Oh, I forgot to write down the final answer here, right? This is 12 kilogram meters squared. Okay, so we can plug in everything into here, and I get 1/2 times 12 kilograms meters squared times 2 radians per second squared. So we end up with kilograms meters squared per second squared, which when you work it out is joules. We can ignore the radians when we're combining it with other units. And so we end up with, when we plug in everything, we end up with 24 joules of energy. So that's how much energy it would take to get these things rotating at 2 radians per second. What if we were to do it again, but like the same 3 balls, but instead of rotating around the y-axis, they're going to rotate around the x-axis. The big difference here is that they are on average further away from the x-axis than they are from the y-axis. So let me number them again real quick. So it's 1, 2, and 3, and we're interested in how far they are from the x-axis. And so you notice that 1 is actually 2 meters from this one, 2 is also 2 meters away, and 3 is 3 meters away. So when we go to calculate this one, the moment of inertia is going to be much larger. Remember, it's the sum of mi ri squared. So we end up with 1 kilogram times 2 meters squared plus 2 kilograms times 2 meters squared plus 3 kilograms, and this 3 kilograms is 3 meters away, so 3 meters squared. When we add all those up together, we get 39 kilograms meters squared. So that's going to give us a larger, it's going to give us a larger kinetic energy. So let's calculate it. It would be 1/2 I omega squared for the kinetic energy, right? So the kinetic energy is 1/2 I omega squared. I plug everything in. I get, let's see, let me quickly do it. So it's going to be 0.5 times 39, which is I, times 2 radians per second squared, and we get 78 joules. So it would take more energy to get these three spheres rotating around this x-axis than it would around the y-axis. We did x and y, why not let's just do z. So consider that they're rotating around an axis that's perpendicular to the page where this red dot is. And so to calculate that, we need to find their distance from the axis. So in this case here, right, they're each a different, we have to calculate their distance from each one. So the distance for 3 is going to be the square root, let's see, of 1 squared plus 3 squared meters, which works out to square root of 10 meters. This one here, R1, is going to be the square root of 1 squared plus 2 squared meters, so it'll be square root of 5 meters. And this one here, R3, will be the square root of 2 squared plus 2 squared meters, so that'll be the square root of 8 meters away. So that's their distances. So if I wanted to calculate their moment of inertia, I add all three of them together just like I did with the other ones. So let's do it. So the moment of inertia will be, remember, the sum of mi ri squared. So it'll be 1 kilogram times r1 squared, which is going to be, since r1 is square root of 5, then it'll be 5 meters squared, plus 2 kilograms times square root of 8 squared, so it'll be 8 square meters. And for the third one, it'll be 3 kilograms times square root of 10 squared, so it'll be 10 meters squared, right? And I add all that together, and I end up with 51 kilograms meters squared. So if I wanted to calculate the kinetic energy in this case, right, it'll be 1/2 omega squared. So plugging in the numbers for that again, it'll be 0.5 times 51 times 4. So it will be 102 joules. So that would be the kinetic energy of rotation for those three spheres around the z-axis. Now, the next thing we're going to look at is over a continuous body, like a solid. You know, if I want to look at the moment of inertia of a coffee cup or a ball or something, what we do is we start with the equation for the individual point charges, or point masses, right? So each little mass, m1, r1 distance. But if we assume that they are infinitesimally small elements, dm, of the whole body, and we want to add up all little dm's of like a whole sphere or something, we can change this into an integral over the whole mass of the body. And you can show that if I just add up all the infinitesimally small bits of mass and add them all up, I can derive this equation here for the rotational inertia of a continuous body. And there's several common shapes that you can easily calculate the moment of inertia for. So they've already been calculated for us. And so using that expression and integrating over the mass over these whole objects, we're able to get the moment of inertia for certain bodies around certain axes. So here is the moment of inertia for 9 commonly used objects. So here, this is the moment of inertia of a hoop of radius r around an axis that goes through its center. Here's this one over here is the moment of inertia for a cylinder. We're going to use this one a lot. Cylinder of radius r and length L and mass m. So all these objects, we assume they have mass capital M. And so here, the moment of inertia is 1/2 mr squared. Here is for a solid sphere, 2/5 mr squared. Here is for a cylinder again, but instead of the moment of inertia through the center axis, it's moment of inertia through an axis perpendicular to it. So we have these common moments of inertia that we will use to solve problems, and I'm going to do a few examples for you. One good example would be, well, let's just calculate a couple for yucks. Let's say I wanted to look at the moment of inertia of a solid sphere. So this solid sphere here, let's say, has a radius of 2 meters, and it has a mass of 9 kilograms. what is its moment of inertia? Well, it's 2/5 from the thing. It's 2/5 mr squared. So 2/5 times 9 kilograms times 2 meters squared. Okay, 2 meters squared. So 2 meters squared is 4 times 2 is 8 times 9 is 72 divided by 5. So 72/5 kilograms meter squared. Let's just, for fun, let's do one more. Let's say I wanted to calculate the moment of inertia around a cylinder here. And it's a cylinder that has a radius of 2 meters, a length of 12 meters, and a total mass of 1 kilogram. So the moment of inertia, this is the moment of inertia through a line through that's sort of perpendicular to the central axis through the center, right? So it would be 1/4 mr squared. So 1 kilogram to m squared plus, then it says 1/12 ml squared. So 1 kilogram, and L is the length of the cylinder in this case, which we said is 12 meters, times 12 meters squared. That works out to be about 1 plus 12 kilograms meter squared. So the moment of inertia in this case is 13 kilograms meters squared. All right, simple calculation for a couple examples. Let's compare two of them. We had the moment of inertia for a thin rod about its center. So if I have a thin rod here, so its radius is so small that you don't need to worry about it, but it has a length L. It tells us that the moment of inertia is 1/12 ml squared. All right, that's the moment of inertia through the center. But then it says if the moment of inertia about the end of a thin rod is 1/3 ml squared. So what's the difference between these two? This one is greater than this one. Now, why is that? Well, this one here, we talked about how the moment of inertia is a measure of how hard it is to spin it, right? If I want to spin this rod about this axis here, it would be easier because on average, the ends aren't that far away from the axis. But this one here, if I want to rotate it about one end, the mass way out here is way further away. So it's going to take more energy to get this thing spinning than to get this thing spinning. If you were to grab a long stick and try to spin it around one end, it takes more energy than spinning it like this through its center of mass, like that. So the big difference is that this one here, some mass is further away. Some mass is further away, and so it's harder for it to get going. All right? Further away, therefore, harder to get going, harder to get moving. So that's why I is larger for that one. Another example here, you would see something similar if you were to compare a thin spherical hollow shell of radius r and mass m to a solid sphere of radius r and mass m. Right? So if you think about the shell cross-section, right? Cross-section. The mass is all on the outside, right? The inside is empty. But if I were to look at the cross-section for here, the mass is everywhere. It's all over the place. So if this is my axis here, right? If this is my axis here, then here the mass is further away. All the mass is a distance r away from here. So it's further away from the axis of rotation. Whereas here, some of the mass is really close to the axis of rotation. So it'll be really easy to spin it. And it'll get slightly harder as it's further out. But some of the mass is closer in, some of it's further out. So this one here is a smaller moment of inertia because it's easier, right? For the solid sphere, it's For the solid sphere, it's 2/5 mr squared, and for the hollow one, it's 2/3 mr squared. All right, so it's more difficult when the mass is further away. Let's just calculate a couple of moments of inertia here for, let's say, two cylinders. They both have a mass of 4 kilograms. The smaller cylinder has a radius of 25 centimeters, and the larger cylinder has a radius of 50 centimeters. So let's write down everything we know here. So for cylinder 1, we have R1 is 0.250 meters, and cylinder 1 has the same mass as cylinder 2, 4 kilograms, and they are both rotating at the same speed of 125 radians per second. By the way, what does that mean? Well, that's approximately, if you were to calculate, it's approximately 20 revolutions per second. So it spins all the way around about 20 times per second. Let's write down the numbers for R2. So R2 is just, everything is the same except it's got twice the radius, right? So M2 is 4 kilograms as well. Omega 2 is the same as omega 1. It's 125 radians per second. And so I can calculate. So now we have everything we need to calculate, right? So I can calculate the moment of inertia for 1. It will be 1/2 m1 r1 squared. And when I calculate, I get 0.0625 kilograms meters squared. When I calculate I2, it's the same except r is 4 times larger. So you're going to get 4 times the answer, right? When I do 1/2 m2 r2 squared, I get about 4 times the answer for 1, so it works out to 0.250 kilograms meters squared. So now I can calculate their final kinetic energies for each of them. So the kinetic energy for 1 is 1/2 I omega 1 squared, and I get 488 joules approximately, and K2 is 1/2 I2 omega 2 squared, and I get about 4 times more. Right? So if these two cylinders have the same mass, this one, and they're both rotating at the same speed, this one has more kinetic energy because it was harder to get it going because some of the mass is further away than the other one. This is an interesting problem from the textbook that I thought would be interesting to do. Trucks can be run on energy stored in a rotating flywheel, with an electric motor getting the flywheel spinning up to 200 pi radians per second. Suppose that one flywheel is a solid uniform cylinder with a mass of 500 kilograms and a radius of 1 meter. What's the kinetic energy of the flywheel after charging? And if the truck were to operate and use up 8 kilowatts, how many minutes can it operate between charging? So let's write down everything we know and then figure everything out here. So we know that the mass of this thing is 500 kilograms. Right? We know that the radius is given as 1.0 meters. We know that it's spinning using electric motor. They get it spinning to 200 pi radians per second. And it's a cylinder, right? So for a cylinder, the moment of inertia, you look it up on that sheet, that table, and it's a 1/2 mr squared. So when I calculate that, that works out to about 250 kilograms meters squared. So for part A, it asks, what is the kinetic energy of this? So kinetic energy is just 1/2 I omega squared, right? So 1/2 times is 250 kilograms meters squared times omega squared, which is 200 pi radians per second squared. And that works out, I'll keep some extra sig figs here, roughly 4.935 times 10 to the 7 joules. So that's a lot of energy stored in the rotational energy of that flywheel. Now it's saying that the truck uses power of 8 kilowatts. So the power used by the truck is 8.0 kilowatts. So 8.0 times 10 to the 3 watts. 8.0 times 10 to the 3 watts. Remember what a watt is. It's the rate at which energy is used. So it's joules per second. All right, and since it's asking us how many minutes can it operate between chargings, I'd like to rewrite this as joules per minute. So I'm just going to add a little conversion factor here. I'm going to say, well, 60 seconds is equal to 1 minute. And I can see how the seconds cancel out, and I'll end up with joules per minute. When I perform that calculation, I get about 4.8 times 10 to the 5 joules per minute. So that's how much energy per minute it uses, is 4.8 joules per minute. And I have a total of almost 5 times 10 to the 7 joules, and it uses about 5 times 10 to the 5 joules per minute. So how many minutes can I run that for? Well, I just start with, well, one way I can write power, it's change in energy over change in time. So the total amount of time is going to be the total energy divided by the power. And so the total energy is the kinetic energy stored in there. So I'm going to put in 4.935 times 10 to the 7 joules. That's the energy stored. And I'm going to divide by and that's joules. And I'm going to divide by the power that it consumes, the rate of the power that it consumes it at, 4.0 times 10 to the 5 joules per minute. I should write minute here. It's not joules per meter. And when I get that, I get about approximately 103 minutes. So that's how long it could consume energy from that flywheel. Now let's look at another way that we can calculate moments of inertia. That chart we had gave us the moment of inertia for several objects, and that moment of inertia for the most part was the moment of inertia through the center of mass of the object. And moment of inertia depends on where you are calculating it, right? Where the axis of rotation is. And so you can show that if I know the moment of inertia through an axis through the center of the mass of an object, I can calculate the moment of inertia through a different axis that is parallel to the original axis. That's a distance h away. So let's say I know the moment of inertia of this weird looking object through this point here, through an axis pointing out of the page, and I want to find the moment of inertia here. You can show that the moment of inertia I will be equal to the moment of inertia through the center of mass plus the mass of the object times h squared, where h is the distance from there to there. So let's just do a sort of a simple example calculation of that. Here's the cylinder, and for the moment of inertia for the cylinder, by the way, we know what the moment of inertia for a cylinder is. Look it up. I'm going to write it as center of mass, and that's in the chart. It's 1/2 mr squared. So let's say I want to find its rotational. I want to find its rotational inertia or moment of inertia around two different axes that are parallel to the original one: the red axis, and the blue axis. Okay, so for the red axis here, the moment of inertia through A, it would be I through the center of mass plus the mass of the object times the distance that the axis is from the original axis squared. So if you look here, this right here is the distance, right? So HA, and that's just one radius away. 4 later, what's the distance of the second axis? HB, it's 3r. So let's plug in what we know. So I center of mass is 1/2 mr squared, and then it's mass times the distance of the axis, which in this case is r squared. So we end up with 1/2 plus 1. I'm going to factor out that mr squared. So the moment of inertia is 1/2 plus 1, so it's 3/2 mr squared. So the moment of inertia to rotate this cylinder through its center of mass is 1/2 mr squared, but to rotate it through an end on the point, through an axis on the edge, it's 3/2 mr squared. And I could do the same thing for the second axis, right? That second axis is further away, so it's actually going to be harder to rotate it because the mass is all going to be much further away. So IB is going to be I center of mass plus the mass times HB squared. So once again, it's 1/2 mr squared, that's the center of mass, plus m, and the distance here is 3r squared. So I end up with 1/2 plus 9, I'm going to factor out that mr squared, like that. And so when you add 1/2 plus 9, you end up with 19/2 mr squared. So that's the moment of inertia through that axis. Let's do another one. This is a box, and I want to find the moment of inertia if I want to rotate that box through an axis at one of the corners of the box. Okay, so we need the moment of inertia through the center of mass. So if I were to rotate it through the center of mass here, right? Here, so this would be the center of mass axis. And that moment of inertia is it's in the chart, and it's for one side is A and the other side is B, and they both have, they're both A is equal to B in this case, right? So it's A is equal to B, so you can simplify this thing here as 1/12 m a squared plus a squared. So a squared plus a squared is 2a squared. Oh, sorry, 1/12. So it's 1/6 m a squared is the moment of inertia through the center of mass in this case. And we can calculate that. So let's write down everything we know real quick. So A is the length of one of the sides, 4.00 meters. The mass of this thing is 10 kilograms. So we can calculate I through the center of mass. So I through the center of mass is going to be 1/6 m a squared. And when I plug everything in, I get 160 kilograms meters squared. So that's the moment of inertia through the center of mass. But I want the moment of inertia through that axis. So I need the distance from the center of mass to the axis. Here's a top view to help us see it. So here's the axis here. In the bottom left-hand corner here, I have a top view. And the distance from here to here is going to be RH, right? So if this here is 2 meters and this is 2 meters, so h is going to be the square root of 2 meters squared plus 2 meters squared. So it's going to be the square root of 8 meters squared. So now I can calculate, so now I have h, I have the center of mass, I can calculate the moment of inertia through that corner. It's going to be I center of mass plus the mass times h squared. And when I plug in my numbers, I get 240 kilograms meters squared. One more example for the road. Let's say I have two cylinders. We're looking at a top view here, and I want to find the axis of rotation around this point here. Well, I calculate the moment of inertia of each cylinder around that point, and I just add them together. So my total moment of inertia will just be, let's call this cylinder 1 and this cylinder 2, will just be the moment of inertia for cylinder 1 plus the moment of inertia for cylinder 2. Okay, what do we need? We need the moment of inertia through the center of mass of each one. They're both cylinders, and we've seen this one before. It's just 1/2 mr squared. So first, let's calculate the moment of inertia for cylinder 1. So moment of inertia for cylinder 1 is going to be I times the center of mass plus the mass times h1. So h1 is the distance from this center of mass here. So h1 is equal to r. So it's equal to 1/2. So moment center mass is 1/2 mr squared plus mr squared. And when you factor and simplify, you end up with 3/2 mr squared. Now what about the second cylinder? That's much further away. It's kind of like before. It's 3r away from its center of mass to the axis of rotation. So h2 is about 3r. So to calculate I2 will be I center of mass plus its mass times h2. So it'll be 1/2 mr squared plus m times, oh, that's squared, m, that's also squared, m times 3r squared. And what do I get? When I collect everything, it looks similar to what we had before, 19/12 mr squared. So now we plug both of those into our total moment of inertia. So just add those two together. So let's see. So this will just be 3/2 mr squared plus 19/2 mr squared. So 3/2 plus 19/2 is 22/2 mr squared. So the total moment of inertia is 11 mr squared. And that's some basics of calculating moments of inertia through axes using the parallel axis theorem.